they are going against the electric field because, that's how you're getting to a higher potential. So then your Laplace and Poisson equations, these are useful for relating your voltage to your charge density, as well as also just figuring out where there's in charge. So these you can think of as the same equation. Laplace's equation is useful for areas that don't have a charge in it. So if you think about it, an area that doesn't have charge, your charge density is going to be 0. So if you plug in 0 as rho v in your Poisson equation, you get Laplace equation. So you get that. And this also comes that, as we just saw here, that voltage is equal to the negative integral of electric field. So if you reverse that, you get that electric field is the gradient of voltage. And the gradient of electric field is equal to negative rho v over epsilon. So there you just plug that in, you get that the second gradient of voltage is equal to negative rho v over epsilon. That's how you get these. Conductors and dielectrics. These are just a little bit of things to know on a conceptual level. Your electric conductors, or PECs, are called for perfect electric conductors. They're usually denoted by this stripe pattern. And inside of them, there's not going to be an electric field. You're going to have a constant voltage. And if there is a charge on it, which there can be, it's always going to be along the surface. So as you can see here, all of this charge is right here on the surface. That's not going to be inside of the conductor. That's just how the charge likes to move around. And you will have a normal electric field, meaning it's pointing, perpendicular to the surface, but not a tangential one. We'll talk about that a little bit when we get to surface to boundary conditions. Now, instead of a dielectric material, you have that, these are your insulators. And what you can see here having this visual is that the individual molecules in the dielectric get polarized when subjected to an electric field. So we can see you can think of this as like a capacitor, 2 parallel plates. One of them is positively charged, one is negatively charged, electric field between the two. The dielectric inside, you can see the molecules, they're being polarized. So now there's an internal electric field that is opposing the larger field from the capacitor. So what this tells you is that whenever you have a dielectric inside of electric field, your electric field is going to be weaker. That you get that from your D is equal to epsilon E. Therefore your E is equal to D divided by epsilon. So D is going to be the same, but your epsilon is going to increase, so your electric field will decrease. It's good to know on a conceptual level. Then boundary conditions. I know some people from Dr. Mahbub's class just got to this, so I'll try to explain this a bit more in depth. In order to do this, you will have to break up your vectors into their normal and tangential components, meaning that you can see here that between material 2, material 1, there's a vector pointing completely perpendicular to that boundary. That's the normal one. And then over here to the side, you have the tangential component, which runs along the boundary. So the things to know with this is that the normal components of the flux density, your D1n minus your D2n, that's going to be equal to the surface charge density. As you can see right there, that rho s, that has to be explicitly along that boundary. There. And the way I like to think of it, for direction, is that the vector is going to be pointing away from the boundary. It's that one minus the one pointing into the boundary, kind of like out minus in. And that's going to be equal to, again, that surface charge density, if there is one there. Then the tangential condition is the electric field. The tangential components, these are going to be the same, running along. Now, again, remember, this is electric field for tangential, and for the normal, it is flux density. I like to remember this by knowing that tangential has an E in it, so you know that, E is for electric field, and that's the one I need to be working with. That's okay.
Yeah, but then
So then this is then from the capacitance of the capacitance of a capacitor. Obviously, you've seen capacitance equal to charge divided by voltage. That's the circuit's way of doing it, but we're in electromagnetics, so we go a little bit more in depth with it. We know that voltage is equal to the negative integral of the electric field, so you calculate that out. I do not have it on here, but we're going to do a problem with that later. And then charge is equal to the charge surface density times the area of that plate. So with that, you get the equation that you're most likely familiar with, which is, I have it right over here. The rho SO times A over the voltage, which from there you can get that's the area times epsilon divided by D, D being the separation between these plates. Yeah. Have you guys gone to electric energy? I know because of the storm, there was a little bit of some class got behind. So I'm not sure if you guys got to energy or even capacitance. Can anyone confirm in chat? But right, electric energy. The main thing to note about this is typing. We did hear this. All right, sure thing. So yeah, for electric energy, we have this little summation that's the energy, obviously refers to work. This is essentially the summation one refers to when you take discrete charges, like test charges once again, and you're moving them from infinity over to a specific arrangement. So when you're doing that, it is 1/2 the summation of the charge of that test charge times the voltage of that test charge that's being applied to it by the charges that's already there. We're going to do a little problem with that soon enough. From there, another important formula to note is the energy stored in a capacitor, which is 1/2 CV squared. We've seen that. Just this other integral that involves you integrate the electric field in terms of volume. The volume is going to be this one, the volume taken up by this capacitor between the plates. All right, yeah, that's all I have in terms of slides. Does anyone have any questions regarding anything they want me to brush over? All right. Here, all right. Do a couple problems if you're on hand.
So if you move the charge already to the right, this,
They are all formulas that we need to understand for exam. Yes, these are all going to be formulas that I'm assuming they could ask you on your exam. I don't make the exam. I don't know what's going to be on it, but they're all important to know. They're important to know because you can test it over them. Let's see. For sure. All right, so let's start with a couple problems. So let's start with one of a coaxial cable. These are pretty common. I had a lot of these in my class. These involve a conductor in the center, as well as a conductive shield.
Yes.
So your inner conductor is of radius A. Your outer conductor is of radius B. There is a dielectric of epsilon 1, which is actually 3 at epsilon naught. And from here, let's see, this inner conductor has a surface charge density of rho s. So from here, the main goal of it is to find. They usually ask find D and E everywhere. So, in order to go about this, the first thing to realize is that there is going to be 3 different regions within this. So, regions. Can you guys see that already before? Is that? Try writing it bigger. The regions. So one of them is going to be when your radius is less than A, so when you're still inside this inner conductor. When A is less than R and less than B, so whenever you're here in the middle in the dielectric. And then for B, when your R is greater than B, so when you're outside. So let's start with, so this is a Gauss's law problem. So let's start with R is equal to A. So we know that surface integral d dot es is equal to the charge enclosed. Now, you think about is charge enclosed. So inside of a conductor, to establish, there's not going to be any charge inside of it. It's all going to be on the surface. So while your radius is less than A, your D here, less than A, is equal to it's just equal to 0. So inside that conductor, there's not going to be anything like that. That's actually a little bit of work. Now let's look at between A and B. So that's all this in here.
Yeah.
That's where the meat of your field's going to be. That's where most of your field's going to be actually. Because
it give out larger maps that is more.
Because now your Gaussian surface is going to be somewhere out here. You're also going to make it a cylinder. This is a cable. Obviously, it's a coaxial cable. So your cable cylindrical. So you're going to want to have a cylinder for this. So your Gaussian surface is going to be a cylinder of radius. Some radius r. The length of it doesn't really matter. Like the height of the cable doesn't matter. Let's just call it a height h.
Yeah.
So now let's find this field. I'm gonna move over to this side now. So once again, setting up our Gauss's law integral. E dot yes is equal to charge enclosed. So okay, so our surface from here is our Gaussian surface. So since it's a cylinder, we're going to want to change the cylindrical coordinates. Okay, gotcha. So I'm swinging chat. Like, oh, what's that doing? All right. So you have your Gaussian cylinder. So you're going to be thinking. So you have radius, you have your phi, and then you have your z. So we are integrating over here. We'll be looking at basically this d of cable, or however long it is, and then also the phi, because you're going to be wanting to go around the whole. You want to go around the whole cable, because obviously you want to get all the electric field that's going around. So for your parameters, just set your phi is equal to 0 to 2 pi over here. Then z is equal to 0, and going to some height h. We just call it h because at the end of the day, it's not going to matter all too much.
Oh yeah, it's fine.
So we have d dot ds, and now hold on, now we're cylindrical, so we can't have ds. We change that to obviously. So since we're in z and phi, we're going to be r dz d phi. Doing r because since you're integrating along this way, you want to make sure you include whatever radial length you're at, so that you get an accurate differential with it. And it's equal to charge enclosed. We'll come back to charge enclosed. By doing this calculus over here, we get so 2 d times h times 2 pi times r is equal to charge enclosed. Now, this charge enclosed, now let's just look at this just out on its own. Charge enclosed on that, we have our surface charge density, our rho s. So that means that charge is equal to rho s times the surface area, just call it A. So surface area of the side of a cylinder is what we're interested in. We don't care about both the circular ends because you're not getting any flux out of that. So it's going to be equal to rho s times 2 pi. It's not going to be r. It's going to be a because all your charge is within this circle radius a. So 2 pi a, this times the height. That's your charge enclosed. And that is once again equal to d h 2 pi r. From there, you just do a little bit of algebra. You get that d is equal to rho s 2 pi a h all over 2 pi r h, which your h's cancel out, your 2 pi's cancel out, leaving you with rho s a little a, not big a. Little a, and being the inner radius, All of that divided by R. Now, it still adds up because as you're going outwards radially, you're expecting your electric field to decrease, or sorry, the flux density to decrease. And then your rho S over A, that's just a constant that just correlates to how much charge is on that inner conductor. So cool, that's going to be, again, keep in mind that that is flux density. If you want to find the electric field from that, you go, E is equal to D divided by epsilon. So that would be equal to rho S times A all over epsilon R. We know our epsilon from here is equal to, your epsilon 1 is equal to 3 epsilon naught. So rho S times A over 3 epsilon naught. Big problem. But that's a good problem. Coaxial cables are good. Now we just need one more region, which is for your radius greater than B. Now, the thing to note about this is that, once again, you're charging. Gauss's law deals with a charge that's enclosed. Now, you think that since you're out, since you're all the way out here outside the cable, you think, oh, you still have all this charge inside. Yes, you do. But this outside, this is also a conductor. So when you're dealing with that, you have to consider the induced charges are going to be moving because of your this. So because of that, your inner conductor is actually going to, since you have a positive charge here, positive attracts negative charges. So all along here, you're going to have negative charges all along this outside conductor. It's usually that's usually referred to as a shield. So because of that, you have all this positive charge along this inner conductor, but then along this one you have all this negative charge. So it ends up canceling out. Meaning, so when you get out here, you're looking at it from like all the way on the outside. Your enclosed charge, it just ends up being net zero because positive and negative, they end up canceling out to zero. So because of that, your D, when your R is greater than B, it's also equal to zero. So we just want to get like a general equation for, so for D, B is 0, R is less than A, and R is greater than B. And when it's N, it would be rho S A over R when A is less than R is less than B. And then I think it's error. So that's for D. Now, the other part of the problem is to find E everywhere, which we luckily only have one of those to worry about. E.
So what were you solving in the first junction? This one
0 still R is less than A, and R is greater than B because there's where the flux of air and rho S over 3 epsilon on R. A is less than R is less than B. You want to ultimately refer everything back to your epsilon naught because that's a fundamental constant. It's not going to depend on anything else. It's just epsilon naught is epsilon naught. Your epsilon 1, epsilon 2, whatever they give you, it's always going to depend off of epsilon naught. So it's always good to return back to those core values that they give you. All right. Any questions for anyone? Anyone?
That should be starting. No, you.
Very cool.
Nothing
from that. Yes. So in that case, let's go ahead and move on to the next part of this problem. Let's see if I can scoot my camera over a little bit to get a camera. Actually, you can't see it at that point. It's fine. So I'll leave it down over there. We have our D and our E down there. Yeah, now, natural extension, you know your electric field. So now, what's next? We need to find the voltage from between points A and B. Typically, so you can think of it. here, and then all the way up here, you have that,
If there's error or input, we will give us.
minus B, AB. You do AB because typically your center, that's like your positive, and then that where this your ground. So you can think of, so let's just find the voltage on that. So V AB, which once again, let's make this, let's make it bigger. Voltage AB is equal to voltage of A. This voltage of B. This is going to be equal to the, again, negative integral from A to the top, B to the bottom, again, because A is, the one with the higher potential. E DL. Yeah, DL. Now, DL in this case, we have to consider, okay, what is DL? This is all working radially, because A and B are also radial distances. So your L, that's just going to become dr. So we can just write that this is as negative beta A minus E dot dr. Which should make sense. You move your camera a little bit. Yes, I can. Just move it over a little bit. Look better. Is that better? Yes. So, all right. So, yeah, that's just negative integral here. So that's again negative integral beta A. So what do we say our E was? Our E is rho S times A over 3 epsilon naught R times dr, which we can factor out our, so rho S or A, 3 epsilon naught, that all factors out. Those are just constants. So that gives a negative rho S times A over 3 epsilon naught times the integral from P to A of 1 over R dr. Now, I'm sure you guys know calculus. That all this evaluates out to negative rho S A 3 epsilon naught times the natural log of A over B. Now, so now, before you say anything, yes, there is a negative sign in front of this. However, you have to consider that, we have A over B. A is smaller than B. So this is going to be a fraction. It's going to be between 0 and 1. And whatever it's, you take the natural log of anything that's between 0 and 1, that's going to be a negative value. So negative times negative, that's going to give you a positive value. You have a positive voltage as we have here. So it still works out. You don't have to worry about that. So that's so that would be the voltage between your center conductor and your outer conductor. No questions in chat so far? Alright, cool. All right. So with that taken care of, let's do. I got one more problem. If there's any, but I can come up with more. If there's anything that you guys have questions over, just drop it in the chat and we can work it. I am here for you. This and now. All right, this one's just gonna be stuff more pure math. So no fancy diagrams for this one. You just have, you can see that. You have some flux density D. In this case, it's going to be equal to x hat. Yeah. Like 4x squared, but it's 4y. So it's not a very standard distribution. It's all weird. It's got multiple variables in it. Plus 1 half x squared plus 2y. So now the question that's asking you here is to find this. Find rho B. Now, obviously, this is just an application of Gauss's law. From the last problem, we're pretty familiar with the the integral version of it. Now it's time to deal with the differential version of it. So we know that divergence of D, this is equal to rho V, and D dot product divergence. So that means that divergence of D, the partial D respect to x. Some problem right? This is not relation. D sub x plus d sub y. See that? Over y. That's equal to okay. So let's look at the x component of d. The x component is just going to be this right here, or 4x squared plus 4y. So we integrate that with respect to x. So obviously this 4y, nothing to do with x. 4x squared, integrate that, you get 8x. Cool. Plus, now we look at the y component. You attach the y. We have 4x squared minus 2y. X squared, we don't care about that. We don't like x today. We're just dealing with this minus 2y, so that gives you -2. Right, go to row B. 8x minus 2 is equal to. So that's your row B. From there, if you want to go ahead and find charge, you can go ahead and analyze that using a Gaussian surface and the integral version of Gauss's law, depending on what your surface want to be. Do you have any questions? Any particular topic anyone wants to cover? Yes, Kevin.
Yeah, if you haven't done one already, would you be willing to do the equation of a line charge over like some infinitely long line charge?
Sure. Yeah, we can do that.
And I have a question in the notes. Take a look at the graph.
Infinitely long line charge. I think I got something.
So that'd be finding the, yeah, so it'd be finding the electric field of an infinitely long line charge.
All right, so Kevin wants to do a line charge. Let's do a line charge.
Infinitely long.
Of course, infinitely long. So let's just print it. Let's just think, z-axis, and we have an infinitely long charge line with positively charged. I think I might not put this as that one here. So cool. So yeah, this is infinitely long. Think of it like a little cylinder. A little cylinder, infinitely long, of positive charge. So we want to find the electric field that thing generates anywhere in space. So another Gauss law problem. So the first thing, what's our surface? So since it's a line, you want to make sure that your surface, whenever there's a flux coming out onto it, you want to make sure it's tangential to your surface at all points. So because of that, you could think of a cylinder. Let me do this so you can get a better look at it. So you have green. So if you have a cylinder, the flux coming out from this line charge is going to be tangential to that at all points. So your surface is going to be a cylinder. Cool. So let's see. Let's just call this radius. One thing to know: radius is just going to be r. Now this is definitely long. So you might think that's a bit of a problem at first, but let's just say that this height. Let's just call this h. Let's just say it's got an infinite height h. For now. And let's just work with that. So you're gonna set a little Gauss law integral. Should probably also know that. Line charge. Got a charge density, surface charge density of rho L along that line. So you're gonna have your D dot ds is equal to your charge enclosed. Now. So let's start with this charge enclosed. Obviously, it's an infinite line. How do you work with that? You just say, you got your rho L, so your linear density times your height h, because if your cylinder is of height h, you should assume that your line's of height h because they gotta match up. So your QAN is now equal to rho L times your height h. Linear, it all works out in terms of the dimensional analysis. Okay, so we got that taken care of. Now, back to your integral. So you're once again dealing with cylinders. You're going to want to convert this to cylindrical units. Hey, your z is going from just say this is c is equal to 0, so the origin all the way up to your z is equal to h up here. So z is equal to 0 all the way up to h. And then since you're a cylinder, you want to get the everything all the way around, all your flux. Your phi is equal to 0, going to pi. We got once again your d. Now again your ds. Since you want to make sure you're capturing the right radial distance at any point, you want to make sure you include that r, d phi, dz. Again, the r just so you can get the right distance, and that is equal to your rho l times h. So again, so then you integrate that out. Get your d times 2 pi. This integral times h times r is equal to rho l h. Now, oh look at that. Now you have h on both sides again. So you divide everything out. D is equal to rho l. Switch. Yeah, your h cancels out. Rho l over 2 pi r. So as your r increases, as you head further out, flux density is going to be less. So if you want to convert this over to electric field, you just divide it. You just divide it by your epsilon, which in this case is just epsilon naught. So you get rho l over 2 pi epsilon naught r. So yeah, it's just the linear charge density divided by 2 pi epsilon naught r. So everybody follow along with that? I haven't seen too many questions. I'm assuming you guys are following. Evan, you got that? Yes. Cool. So yeah, you can use the same technique whenever you're analyzing an infinite plane of charge. So if you're close to like a capacitor, we were really close to one of the plates, you can assume it's infinite. In that case, obviously you have your height, your length h, and then your width w, which are both infinite. But you'd have the same thing happen. They would still cancel out, leaving you with a relatively nice answer. Okay. Have any more questions for me? Any other topics? Person? All right. So that's just about it. That's just about what I have for today. I am available on Wednesdays from 1 to 3 here in the IEEE room for tutoring. And I will also be here tomorrow night at around 5:30. If anyone wants to come in and ask any more questions, I will be here available. Okay. We got a question, Jeb. For sure. So yeah, I'll be available tomorrow at 5:30 and then Wednesdays at 1 p.m. if you guys are available. If not, I'm also on Discord, so just go ahead and text me there. Will this be recorded? Yes, this is being recorded. It will be up on the IEEE Discord and the YouTube channel sometime soon after this. All right, thank you. You have a great day too. Welcome.